Good day everyone! Today my partner and I will discuss to you the continuation about Reynolds' transport theorem. So here are the things to be discussed. First is fluxes, second is mathematical formula, third is application, and lastly is the integral form and differential form of Reynolds' transport theorem. So now let us first discuss fluxes. Flux refers to the flow rate of a quantity such as mass, momentum, or energy across the boundaries of a controlled volume, meaning fluxes are integral components in Reynolds transport theorem as they account for the movement of a quantity across the boundaries of a controlled volume. First type of fluxes in Reynolds transport theorem is the mass flux. So this term represents the rate at which mass is transferred across the control surface. Mass flux is used in the continuity equation which expresses the principle of mass conservation. Given is the basic mathematical formula for mass flux, which is m is the mass flux, mass flow rate per unit area. Rho is the density of the substance in kilogram cubic meter for international system units, and V is the velocity of the substance perpendicular to the surface in meter per second. So the importance of mass flux in fluid dynamics is that it describes how much fluid passes through a surface, helping engineers design efficient systems like pipelines and ventilation. Imagine a river flowing through a dam. Mass flux would quantify how much water, or the mass, flows through each square meter of the dam's surface every second. This allows engineers to assess the load on the dam and understand the river's behavior. Another type of flux is momentum flux. This term represents the transfer of momentum across the control surface. This flux is essential for applying Newton's second law to a fluid system, which helps determine forces on objects within the fluid. Momentum flux is calculated based on the density, velocity, and momentum of the particles. For a fluid flowing with density and velocity, the momentum flux can be expressed as that. Real-world application in the design of aircraft, momentum flux helps engineers analyze how air flows over the wings and produces lift. By understanding the momentum flux, they can optimize the shape and surface of the wings to maximize efficiency. Last type of flux is the energy flux. This term represents the rate at which total energy is transferred across the control surface. This term describes the transfer of total energy, internal and kinetic, across the control surface due to fluid flow. For a fluid or radiation moving with velocity and energy per unit volume, the energy flux across a surface can be expressed as that. E represents the energy density, energy per unit volume, which could include kinetic, thermal, or radiative energy. V is the velocity of the energy carrying substance, or the speed of wave propagation in the case of radiation. Mathematical formula of Reynolds transport theorem states that B is system total amount of the extensive property in the system. CV is the control volume, a fixed or moving volume in space through which the fluid flows. CS is the control surface, the boundary surface of the control volume. P or rho is the fluid density, mass per unit volume. B is the intensive property per unit mass. V is the velocity vector of the fluid. N is the outward unit normal vector to the control surface. dV is the differential volume element within the control volume, and dA is the differential area element on the control surface. So this is the explanation terms. The left side represents the time rate of change of the property within the entire system, which is moving with the fluid. The first term on the right side is the rate of change of within the control volume, taking into account any time variation of the property due to fluid movement within the volume. Second term on the right side represents the net flux of across the control surface. The dot product indicates how much of the property is moving across the surface in the direction of which is the outward normal vector to the surface.
Applications of Reynolds transport theorem.
So first, the fluid flow in pipes and ducts. In systems like water distribution networks, oil pipelines, or HVAC ducts. The RTT helps analyze the rate of flow of mass, momentum, and energy.
As you can see in this video, The A1, the V1 is the inflow, and the A2 and the V2 is the outflow. This is the example of flow in pipes.
The applications of fluid flow in pipes and ducts. Engineers use RTT or the Reynolds transfer theorem to calculate the amount of fluid, mass flow rate, entering and leaving sections of the pipeline, allowing them to ensure the system's integrity and efficiency. So for example, RTT helps to determine how much pressure is required to maintain a desired flow rate across a pipeline. So next, practical applications is the blood flow in biomedical engineering. In biomedical applications, understanding the flow of blood through vessels and organs is crucial. The RTT helps model blood flow and analyze how it changes across different regions of the circulatory system. This is valuable in designing medical devices like heart pumps and understanding pathological conditions such as blockages or aneurysms.
In aerodynamics, RTT helps analyze the forces acting on aircraft wings and other components. By applying RTT to the air flowing over an aircraft wing, engineers can calculate lift and drag forces by evaluating changes in momentum as air passes through the control volume around the wing. This is critical for optimizing wing shape and achieving desired aerodynamic performance. Another application is in hydroelectric power generation. Hydroelectric dams use the flow of water to generate power. RTT helps in assessing the transfer of energy from water to the turbines. In a hydroelectric dam, RTT is used to calculate the kinetic and potential energy of water as it flows through the turbines. This allows engineers to estimate the power output of the dam and optimize turbine design for maximum efficiency.
Integral and differential form of Reynolds transport theorem.
In the integral form of Reynolds transfer theorem, this equation states that the rate of change of property within the control volume is equals to the net flux across the control surface. When this relationship equals 0, it indicates a steady state where the property is conserved in the control volume.
Consider a control volume around a section of a pipe through which an incompressible fluid with a constant density P flows. The fluid enters the control volume through the inlet with a velocity Vn and exits through the outlet with a velocity V out. Assume the flow is steady and there is no accumulations of mass within the control volume. This demonstrates that under steady flow conditions, the mass within the control volume remains constant, confirming the conservation of mass principle. The integral form of Reynolds transport theorem effectively describes how the mass entering and exiting a control volume is balanced.
And now, I will discuss the differential form. The differential form of the Reynolds transport theorem provides a way to relate the rate of change of a property of a fluid within a control volume to the flow of that property across the control volume's boundary. This term represents the local rate of change of a property within a control volume over time. If we are considering mass, this term would represent how the mass within the control volume is changing at a specific point in time. Next, this term represents the divergence of the mass flux, indicating how mass is flowing out or in the control volume through its surface. Last, setting the sum to 0. The equation implies a balance. The local rate of change of mass within the control volume, the first term, local the net mass flux across the control volume surface. The second term is 0. This signifies that the mass flow into the control volume is equal to the mass flow out, ensuring mass conservation. So the differential form, it is illustrating how changes in fluid properties within a control volume are balanced by the flow of those properties across the boundaries of the volume. This is essential for analyzing fluid behavior in various applications such as pipe flow, aerodynamics, and more.